Hi, my name is Daniel Logue, and I'll be presenting on the Flying Octopus's work on the carbon fiber spar manufacturing for the Upturn human-powered helicopter project. The team consists of myself, a manufacturing engineer, and 5 mechanical engineers: Jason Adley, Sterling Fuentes, Graham Garvin, Kenny Garodin, and Timothy Lipsky. We work closely with our project advisor, Dr. Joseph Mello, of the Mechanical Engineering Department, and the advisor for the Human-Powered Helicopter Club, Dr. Kurt Colvin, of the Industrial Manufacturing Department. Over the course of this presentation, I'll go over the background of the human-powered helicopter, the design of the spars, the manufacturing of the spars, and the assembly, testing, and integration with the other project components. The Upturn was donated in the fall of 2012 by Cal Poly alumni. The Aircraft Design and Construction Club, or Human-Powered Helicopter Club, has worked on optimizing the Upturn's components in order to win the Sikorsky Prize. Sikorsky Prize requirements are for a human-powered helicopter to hover for 60 seconds, stay within a 10-meter square, and exceed 3 meters of altitude. The Flying Octopus team was tasked with optimizing the spars to assist in flight success. The team would design and duplicate a set of spars that would match or exceed the performance while reducing the overall weight. To do this, the team developed a system of carbon fiber spars, which allowed similar interfacing with the other helicopter components. The team developed and documented all manufacturing processes so the Human-Powered Helicopter Club would be able to replicate the design for future projects. So what are spars? Spars are the skeletal structure of the helicopter, making up the wingspan and providing support to the rotors, which give the helicopter its lift. On the Upturn, the spars are attached directly to the cockpit, where a human pilot sits in a recumbent bike seat to spin up the propellers to rotate the wings. The spar system consists of 12 spars, including 3 different sizes: 3-inch diameter, 2.5-inch, and 2-inch diameter, and lengths ranging between 8 feet and 12 feet long. The spars experience several different forces during flight. They are subject to shear forces from the weight of the landing gear, bending forces from the weight of the spars and the rotors, and a torsional force from the drag and lift created during flight. The team looked into a variety of manufacturing processes before deciding on a pre-preg layout. All carbon fiber consists of a bonding between a matrix and reinforcement material. Pre-preg eliminates a separate bonding process as the resin is pre-impregnated into the carbon fiber. It yields higher quality parts as there is more control of the resin application, and the stiffer pieces of fabric are easier to handle than wet layup applications. The spars use unidirectional cloth applied in multiple layers axially and at alternating 45-degree angles. The carbon fiber is cut into strips and wrapped around a mandrel. The mandrel gives the carbon fiber its shape and offers support during the curing process. The mandrel must withstand the curing temperatures of 250 degrees Fahrenheit while remaining rigid. It must be able to separate from the spar after curing. We wanted them to be reusable to save on setup times and costs, and be safe, avoiding any hazardous materials or processes. The team decided on using aluminum as it is commercially available in multiple sizes, does not bow at high temperature, and has a sufficient thermal expansion to allow for easy removal of the spars. The mandrels were also within our budget of $750. The aluminum mandrels underwent a long pre-layout phase of sanding. This was necessary to give our finished carbon fiber the required surface finish, as well as to make it possible to remove the cured carbon fiber from the mandrel. To aid in this procedure, a rotary fixture was developed, so the mandrel can be suspended and rotated by hand. This included custom inserts for the 3 different sizes of aluminum. Here's a close-up view of the original aluminum on top and the finished aluminum on the bottom after sanding. After design, a layup process was developed which could be repeated for all spar sizes. The layup process requires several operators to ensure acceptable application. The rotary jig was repurposed for this task without any modifications. Once the process was tested, the Flying Octopus team recruited club members from the Human-Powered Helicopter Club to take over the manufacturing. This allowed for the manufacturing to proceed in tandem with the development of the next phase of operations. This was the first step in knowledge transfer to the club in order for them to be able to replicate our processes. After all the carbon fiber is layered, shrink tape is necessary to apply even pressure during curing. It also helps prevent wrinkles and bleed out of the resin. After testing, we found that applying a high tension and high overlap of the shrink tape yielded the best results. Due to the size of the spars, we were unable to use the autoclave on campus. We instead used a custom oven from a local carbon fiber enthusiast in Los Osos. The spars are slowly raised to 250 degrees Fahrenheit, kept there for 20 minutes, and then allowed to cure. To remove the spars, holes were drilled through ends of the mandrel. After curing, a rod would be placed through this hole and locked in a vise, so that the spar could be manually pulled off of the mandrel. The cured spar would then be ready for the post-curing processes. The first of these processes is sanding. This gives the spar its desired surface finish and outer diameter, as well as remove any excess shrink tape. This operation used a belt sander and a multi-purpose rotary jig. The spars were then cut to length using a tile saw. A dowel was placed inside to offer internal support to avoid splintering or cracking. The last step in the spar manufacturing was drilling holes. The hole placement is dictated by the interface with the rotors, cockpit, guide wires, landing gear, controls, and propellers. Just like in the cutting operation, a dowel is placed inside the spar to reduce cracks. Once the spars were complete, they would need to be interfaced with each other to construct a complete spar structural layout. This involved designing and producing 4 different joints for each of the 4 present connections in the design. The 3-inch to 3-inch diameter joint, a 3-inch to 2.5-inch diameter joint, 2-inch to 2.5-inch to 2.5-inch diameter joint, and a 2.5-inch to 2-inch diameter joint. The same diameter joints, the 3-inch to 3-inch and 2.5-inch to 2.5-inch, would use a carbon fiber sleeve. This is placed on the inside of the spars and epoxied into place. Holes could be drilled in the sleeves as required for integration. The 3-inch to 2.5-inch joint used a carbon fiber bottleneck sleeve. Like the same diameter sleeves, these fit on the inside of the spars and epoxy into place, leaving a curved feature to ease the transition of the 2 diameters. As it is only 2 feet long, we used a polypropylene mandrel, which was machined on a CNC lathe to achieve the feature. It was wrapped in carbon fiber and cured in autoclave and Cal Poly composite slot. The 2.5-inch to 2-inch joint uses a system of bushings and collars. These were machined out of polypropylene. 2 bushings are epoxied onto the outside of a 2-inch spar, on either side of a collar, which is epoxied to the inside of a 2.5-inch spar. This system allows the last section spar and rotor to rotate freely to change the angle of pitch, as designated by the control system. Quality tests are performed by assembling each entire wing section onto a test fixture. This would allow us to resemble in-flight conditions in order to test for part failure before assembly of the completed helicopter. The final phase of the project is integrating with other project teams. This includes interface with rotors, cockpit, guide wires, controls, landing gears, and the propellers. The Flying Octopus team has completed the spar manufacturing and is currently working on integration with the other teams. Once integration is complete, the helicopter will be ready for test flights. The team has developed a manufacturing production plan to hand over to the club to enable future replication. This project showed the effective use of a multidisciplinary team. By working in tandem with the designers, prototypes, fixtures, and tooling could all be prepared to ensure a timely production schedule. Thank you for watching, and I hope you enjoyed this presentation.